We are in chapter 9. This is section 9-5. This is recording number 2. Okay, and what you're going to see here is that those tables give you the alpha values. If it's a two-tailed test, remember what the alpha value is. That's your error budget. That's what percentage of the time are you willing to be wrong. So if you say I want an alpha of 10%, you're wrong 10% of the time. If it's a one-tailed test, you just use that table as it is. But if it's a two-tailed test, well, implicitly, when you draw that cartoon, what you're always going to be doing is you're going to have two tails, so your alpha is split in half. Half of the error budget is on the right-hand side, the right tail. Half of it is in the left tail. So that's what he's talking about here when he says, well, you have to use the alpha over 2 value in that table. Okay, so if you have a two-tailed test and you want alpha is equal to 0.05, well, then you would look at the table for 0.025 is the table you would use. If you had an alpha of 10 and it was a two-tailed test, you would look at the table for half of 10, which is 5, so you'd look at the table for 5.05. Okay, all right, so here's an example. Find the critical value right-tailed test. Alpha is 0.05. The degree of freedom for the numerator, yes, DFN, is 15, and degree of freedom for the denominator is 21. So he has it right here, but I think it's more useful if I go to the actual table, so I'm going to do that. Okay, so this is alpha is 0.01. This is alpha 0.025. 0.05. This is the one we're looking for right here. Okay, so let me see if I can make this a little bit bigger. But if I make it too big, then you're not going to be able to, it won't fit in the screen. Just give me a minute here. Okay, so, to find the critical value, first of all, you go to the appropriate table. And the table it's in this table H, but there's several in that group of tables. So it's absolutely critical you go to the appropriate table. This is alpha equal to 0.05. Then you want the degree of freedom of the denominator. That's over here. Okay, and it says that the degree of freedom for the numerator is 15, and for the denominator is 21. So we want degree of freedom of denominator of 21, that's right here, so this is the appropriate row, and it says the degree of freedom for the numerator is 15, so that's 15, that's right here. So it's hard for me to do it on the screen. Easy if you have both of your hands, you can just put your fingers on there and you bring this finger down and you bring the other finger across and you end up right here at 2, let's see, I'm sorry, it was 21 and 15, so 21, come across here, and 15. Boy, it's hard to do on the screen. So that's 2.18. That's it right there. So let's see if I got that right. Let's see here. Okay, and we got it right. It's 2.18. So that's the critical value. The critical value for this example. Okay, so he noted before, when you use the f-test, the larger variance, that's the big brother, he's always on top. Okay, if you're conducting a two-tailed test, alpha is split. Okay, so if it's an alpha of 10, you find the value on the table, you find the 0.05, because these tables are for the right tail test only. Okay, and then when you're conducting the two-tailed test, we'll see in a minute, you only use this right tail. And the reason for that is because the f-test value, which is right here, these are positive numbers, the big guy's on top, so the big guy's on top, this ratio, this fraction is going to be bigger than 1. Okay, so that's why he says the f-test value is always greater than or equal to 1. Okay, so we want a two-tailed test, alpha is equal to 0.05. Okay, numerator is 21, so that means the degree of freedom for the numerator is 20. That's the top guy is 20, and the sample size for the variance of the denominator, that's the degree of freedom of the denominator is over here, is 12, so that degree of freedom is 11. I may have said that wrong. It's the sample size is 12, so the the degree of freedom is 1 less. It's 11. Okay. Okie dokie. So we have. So we got it. This part's easy. This row, this column. The hard part is remembering which of these tables do you look at. And since it's a two-tailed test, we're going to take half of the total alpha. The total alpha is 0.05. So half of 0.05 is 0.025. So that's the table we're going to use. Okay. So what he says here too is, hey, listen, if you don't have this exact degree of freedom, the closest smaller value should be used. So we get down here, down towards the bottom. Okay, let's say it was 35, or let's say, like 32. Well, 32 is not there, so we use the closest value, which is 30. Okay, let's see where that's at. Okay, so I want you guys to look at this. Follow what he's saying, look at the table, and make sure you understand it, okay? All right. Okay, so these are the kinds of hypotheses that you're going to be using. It's always going to be the same. It's always going to be that the null hypothesis is that they're equal. The right tail test, left tail test, and a two-tailed test. I don't recommend trying to memorize this. To me, it's better to just develop your intuition so you don't have to memorize it. You just understand it, okay? Okay, so here's the key points. Top guy, big guy is always bigger. If it's a two-tailed test, you split or divide into the alpha value. Okay. Obviously, if you are dealing with standard deviations rather than the variances, just remember by the definition of standard deviation, you do the variances, you have to square them, and that's the F-test. The F-test is the variance on top of a variance. So you gotta make sure that you have the variances. Okay. And then here's the rule about how to find the degrees of freedom. Okay. All right, so there's a couple of assumptions that have to be made. This test doesn't work if these aren't true, and that is that the samples have to be random. That's almost always true. I can't think of when it's not true. This is kind of weird. The populations have to be, well, they have to be normally distributed. That is common, or it has to be at least, it doesn't say approximately. It says a test should not be used when the distributions depart from normality. So I guess it has to be pretty darn close to being a normal distribution. Almost everything is, so it's not that big a deal. And then the samples have to be independent of one another, okay? All right, so let's take a look. It's the same process as before. I'm going to let you read that in your book, okay? Okay, here we go. This is what I was looking for. This procedure is not robust. Robust means it can withstand imperfections. It is not robust. It cannot withstand imperfections. Minor departures from normality will affect the results of the test. So this test should not be used if the distributions depart from the normality, because the standard deviations are not a good measure of the spread in a non-symmetrical distribution. We have Chebyshev's theorem that gives us an idea of how things are spread out if you have a standard if you know the standard deviation. You don't need to know very much. But hey, that's the rule. There's other things you can do, which we're not going to get into if it's not normal. Okay. He says the reason is that standard deviation is not resistant to outliers or extreme values. So what happens in real life is the researcher will look at his outliers and he'll just say, well, that was a measurement error, or that was a problem with, whatever it happened to be. I'm going to just toss that data point out. So that's what happens in real life. Okay, so let's take a look here. We get the heart rate of smokers. We want to find out, is the variance of the heart rates, the variance, not the average, the variance of smokers, is it different from the variance of heart rate of people who do not smoke? You get the two samples. Okay, the first sample is 26. The second sample has 18 data points. You do the calculations, and boom, this is what you come up with. Okay. We're going to use alpha is equal to 0.05. Is there enough evidence to support the claim? And you assume that it's normally distributed. Okay, so null hypothesis is always the same. We're assuming the variances are the same. That's our hypothesis. The research hypothesis is saying, nope, it's not true. They are not the same based on this data. You could not, the researcher is saying is, you could not possibly be the same variances. I picked these guys at random. They are so different. I mean, for crying out loud, look at this. This one's 36, this one's 10. How could it be the same, right? That's your intuition, okay? All right, so it's a two-tailed test. So if alpha is 0.05, we're going to use the 0.025 table. Okay, so you got the degree of freedom, you go to that table and you get this critical value of 2.56, okay? All right, so 2.56, that's my critical value. That's the one I'm going to be paying attention to. Now, I know there's another one over here, but I don't know what it is based on these tables. I don't care because I'm only going to use this one. I compute the test value. I get 3.6. That's right in here somewhere, right? This is so unlikely. 3.6 is so unlikely that you would get that we are going to say, you know what? They are not the same. The null hypothesis is incorrect. It is not true that the variances are the same for smokers and non-smokers. There's a much bigger difference. And let's see, hang on one sec. Okay, and just as an editorial comment, this kind of makes sense. I mean, smokers have a higher variability because smoking affects all kinds of things in your body. And certainly, for you nurses out there, correct me if I'm wrong, but a normal sinus rhythm is what all of us want to have on our EKGs. You don't see that with smokers. They have they don't have a normal sinus rhythm. So it affects their heart rates, it affects their pulse rate, and therefore you're going to expect to see a larger variance in the smokers. So this passes the sanity check. It kind of makes sense that you would get this result. Okay, so there's a good example, as good as any. All of these examples are going to be basically the same. We're going to go through the same routine, so if you don't mind, I won't bother to do it. It's a one-tailed test up here that says they want it to be a one-tailed test. Alpha is 0.01. Okay, so at 0.01, we look at the tables. Here's our critical value. We do our test value, gives me 1.99. That's down here. Therefore, it's not out here in the critical region. Okay. Okay, so that pretty much wraps it up as far as the traditional technique. Okay, so now the so-called p-value test. Remember, the p-value is where you take this test statistic that you calculated here, and you say, based on that test statistic, what is the corresponding probability of getting that number or more? What's the probability of getting that test value right there, 1.99 or more? So here or more. That's what a p-value works out to be. Now, in real life, it's all done on the calculators or on the web programs. We're trying to learn how to do this using the tables. Trust me on this. It's worth doing a few times just to kind of get the idea, and it helps you understand the tables. But in reality, it's going to all be in the programs that you're going to use. And I don't have enough time on this last recording, so I'm going to stop this recording, and I'll do one more recording, and we'll cover this material.